It's my pleasure to introduce Dennis Lehmkuhl, who's the chair of natural philosophy and philosophy of science, and the Lichtenberg professor of history and philosophy of physics at the University of Bonn. Today, he's going to be talking to us about what does it mean to be a realist about dark matter and black holes. And this is the first in our three-part series on dark matter, which will culminate with a panel discussion at the end.
In the fourth one.
In the fourth one, yes. So there'll be 3 talks and then a panel discussion. Thank you, Dennis.
All in this semester?
Yes.
Yeah.
That'll take us through to the end.
Okay, well, thank you very much. Thank you very much for the invitation, and thank you very much for, well, having me. It's a great honor. And yes, so I'm supposed to kick off the series on dark matter, and I'm going to speak about what it means to be a realist about dark matter. And I'm going to approach this by comparing that question to the question of what it means to be a realist about black holes. And so I'm going to start with dark matter, then go over to black holes, back to dark matter, comparing the two, and then come to an assessment of the guiding question. So just to start off and very quickly, what everybody tells you, what everybody tells us is that only 4.9% of the matter content in the universe is constituted by ordinary matter, 26.8% by dark matter, and 68% by dark energy. And here is a picture of a galaxy with a dark matter halo. And some try to convince you that this is an ad hoc assumption, that it's only a way of trying to rescue general relativity and its Newtonian limit via the introduction of dark matter. And others even ask, what does it even mean to speak of dark matter? Is the concept, is the word thick enough? Is it clear enough what it means to even make such a statement that dark matter exists? And so my talk will be focused in a way on this question: what does it mean? And is it a concept that is thick enough to be sure whether it refers to something that exists? And then to answer the question whether it actually does refer to something that exists. And the way of asking that question was pioneered by Niels Martens in a great paper of 2022. And Niels asks, so should we believe that dark matter exists? Or in different words, should we be realists about dark matter? And his diagnosis was that we don't yet know enough about what the term, the concept dark matter refers to in order to be realists about it. So the word yet is quite crucial in that paper, right? He does not say that it will stay like this, but his claim is that at the current moment, we don't have a clear enough narrowing down of the concept of dark matter to know whether the term refers to something in the real world, and thus to be realists about it. My question is slightly in the neighborhood of that question, because I think the should we believe that doesn't leave enough wiggle room for reasonable people to disagree, right? And so what I want to ask is it reasonable to be convinced that dark matter exists? Is it reasonable to be a dark matter realist? And my diagnosis is that we know a bit more about dark matter than it might appear, and in fact enough for it to be reasonable to be a dark matter realist, even now, even at the current state of knowledge. But that we don't know enough for it to be unreasonable not to be a realist about dark matter, right? Hence, reasonable people then can disagree. And I contrast this, or I assess this statement, justify the statement by looking at the corresponding question about black holes. So asking, do we know enough about the concept of a black hole to be realists about black holes? And there I argue also, yes, it's reasonable to be a realist about black holes, to believe that black holes exist. And in comparison to the dark matter case, though, I argue that it would be less reasonable not to be a realist about black holes compared to the reasonableness of not being a realist about dark matter. And basically the talk is going to be about justifying these differences. Okay, the structure is given by the following outline. I'll first review Niels's central claim about dark matter, and in particular where his diagnosis that the term isn't thick enough to refer and for us to be realists about it, where it comes from. Then I shift the question a little bit to ask whether we have sufficient evidence for it to be reasonable to believe in the existence of, and thus to be realists about, black holes on the one hand and dark matter on the other hand. And so a lot here will be about how much evidence and what type of evidence is necessary to believe in the existence of something, in contrast to a feeling that you have a clear picture of what it is, or a comprehensive view of what all its core properties are. To what extent can you believe in the existence of something, even if you're very aware that there's all kinds of properties of that entity that you don't know yet? And I compare the case of black holes and dark matter with each other in that regard. And then compare the evidence for black holes and dark matter and come to the conclusion that it is reasonable to be both a realist about black holes and dark matter, and also reasonable not to be a realist about them, but that it's less reasonable to be not to be a realist about dark matter than it is with regard to black holes. Okay, so first to Niels's central claim about dark matter. He distinguishes between three types of concepts of dark matter. And so he gives first an example for a maximally thick concept of dark matter. Example because it zooms in on a particular model of what dark matter could be. And that example is a single type of supersymmetric weakly interacting massive particle with zero hypercharge, a mass of 2.8 TeV, an annihilation cross-section into standard model vector bosons of this, no further self-interactions, and a cosmic density corresponding to a contribution of 27% to the total cosmic energy budget. And so here he says, well, if we knew that, right, if we knew this is dark matter, then yes, this is definitely thick enough to be a realist about it. If we find that this actually refers. Yes.
Where is he pulling this candidate out of? I work on dark matter and I've not seen this as a compelling candidate with this entire combination of properties, including mass. So anyway, just a question.
I mean, given that he's here, I could pass this on. I don't think he refers. Niels, do you want to say something about this?
Well, I think the honest answer is that at that point, Dennis was my boss and the other boss was a particle dark matter physicist, and it was in one of his papers. But my point was not at all like this is a reasonable candidate. It's just this was an example of something where all the parameters have some value. I'm not in no way thinking that this is the best or even a good dark matter candidate. It's just a specific one. That's the only point.
Yeah, and it's clearly said in the paper, right? It's one example of, and it's supposed to be an example of thickness, not primarily of the best conceivable candidate, right? But just a well-defined.
Whether you take something that is astrophysically as plausible, the most plausible as your thickest example or not. I let this go, but I'll let you continue. But it doesn't matter what you take to as an illustration. You can take something like, that is for thickness. If it doesn't really correspond, anyway. I think it's going to get more animated as we go on, so I'll let this one go.
Okay, thank you. I mean, fortunately, at least for me, I'm not going to base the further discussion on that one, but on another of his dark matter. Yeah.
Right. Yeah.
Right. So that's the example, maximally thick concept. Then on the other side of the line, what he considers the thinnest possible common core concept of the term dark matter is stuff that either contributes 27% to the total cosmic mass energy budget or acts as if it does so, thereby being responsible for certain gravity-mediated observable related to structure formation clusters and galaxies. Now, this is indeed so thin that even extra gravitational degrees of freedom would fall under that conception of dark matter, right? And so here Niels says, well, clearly this is not thick enough a concept to be able to refer. It's so thin that it could basically always be made to fit. And so it ends up being vacuous. And what he ends up spending most of the paper on, and what I will take also as my starting point, is what he calls the intermediate thin common core concept of mainstream dark matter, which all or most mainstream dark matter models in particle physics are associated with, which is defined as a massive field with a contribution to the total cosmic mass energy budget of 27%, thereby being responsible for certain gravity-mediated observables related to structure formation clusters and galaxies. In case it is a particle, so it's an if, right? If it is a particle, its mass is roughly between 10 to the minus 22 and 10 to the 13 electron volt. And so especially here, because it's so unclear in what mass range these particles are, and also because not that much is in here, he ends up arguing that the thin common core concept, not to mention the thinnest possible common core concept, but also the thin common core concept, is too thin to be justified, for us to be justified in being convinced of the existence of dark matter, and thus to be a realist about matter. And then he has a beautiful sentence in the paper saying, to be a realist about the unknown is not to be a realist, right? If you don't really know what this refers to, if you don't know enough about it, then saying you're a realist about it becomes vacuous. So much of my talk is going to be about the question whether this is really the thin common core concept of mainstream dark matter, or whether there isn't more that we know about a common core concept of mainstream dark matter beyond what is here, and whether that changes something about this assessment. So in fact, so I will speak of the observationally relevant common core concept of dark matter as that which adds to the above the following claims. Dark matter interacts gravitationally. That is sort of contained here when it says thereby being responsible for certain gravity-mediated observables, but it's not completely clear what the coupling structure is. But dark matter interacts gravitationally, just making it explicit. Then something that is not in here is that dark matter does not interact via the electromagnetic interaction, hence the name dark, right? And dark matter does not interact via the strong interaction and may or may not interact via the weak interaction. I think it's fair to say that that dark matter models have that in common too. And on top of that, if one goes beyond just the observationally relevant common core concept and goes to the dark matter concept that is inherent in lambda CDM, the standard model of cosmology, then the following modifications come in. So in addition to the observationally relevant common core concept of dark matter, we have dark matter interacts gravitationally.
Quick clarification.
Sure.
In the thinnest common core concept of dark matter, is there a reason why you have not used the word it's a particle, although you said it interacts gravitationally?
Yes.
You have not used particle?
Yes, that's conscious.
Okay.
Yeah. And I'll come back to that. Thank you.
Okay.
Yeah. In lambda CDM, added to this is dark matter interacts gravitationally like a collisionless fluid. So that's a very, very strong constraint to what I said before, right? It really says how it interacts gravitationally, what kind of gravitational source it is. Then to the second part of the previous one, we can get, so dark matter does not interact via the electromagnetic interaction. I could have put this as a separate bullet point. Given this, the first property, that it acts like a collisionless fluid, and the standard model of particle physics, it follows that dark matter must be non-baryonic, right? So further, a very strong constraint of the term dark matter within lambda CDM. Those two stay, and the final two, I think, are really specific of dark matter in lambda CDM, and they're different from the above constraints, because they're not really about something that is inherent in the concept or in the notion of dark matter. They are constraints about the dark matter that is present in our universe in particular, as described by lambda CDM, right? They leave it open that in another universe for which a different cosmological model would be the empirically adequate one, these two might not be fulfilled. So for our universe, the dark matter moves slowly, hence the word cold in CDM of lambda CDM, and only the total proportion of dark matter in a given system is specified. So lambda CDM by itself does not demand that dark matter is made up of particles. It could be a fluid. And based on essentially this explication of the dark matter concept of lambda CDM, I found, after I'd written down that slide,
You
that
are arguing, sorry, could we go back to that list, please, again?
Sure.
The observationally, we know it's not a fluid. Observation,
in the cosmological domain,
yes, in lambda CDM, fluid, as a fluid, it's ruled out. There are many observations that tell you it's not an actual fluid. It is like a fluid, but it's not a fluid.
so that's
it's
compatible with what I
possible.
say here, right?
Right.
Like
But-
a colorless fluid?
Yeah, but I think I do have a problem with the fact that, okay, I mean, collisionless particles is where I would say observationally we fall. But anyway, you can keep going. Yeah, I think that may not matter in the end, but
Okay, thanks. I might ask you more about this though later.
Yeah.
Thank you. Okay, so in a great, very recent paper from this year, Weinberg provides an analysis arguing that realism about dark matter is justified by arguing that the term dark matter as it appears in lambda CDM is thick enough, is semantically thick enough to fulfill the tracking requirement of Psilos's causal descriptor theory of scientific reference for theoretical terms. Essentially, that the way that the term has been used and is used in lambda CDM across different domains, empirical domains, and experiments is thick enough to argue that the definition just given corresponds to what is empirically confirmed, tracked referentially across these different applications. And thus, Weinberg concludes that it is justified to be convinced that dark matter, as described by lambda CDM, actually exists, and that hence it is reasonable to be a dark matter realist. And I find his arguments very convincing. Still, the argument relies on presupposing Psilos's account of reference, and I'm going to try in the following to argue that even if one does not presuppose that account of reference, or indeed any specific account of reference, one can conclude that it is reasonable to be a dark matter realist. And so I ask you, it all comes down to the question, how much do you need to know in order to know that something is there? So I'll ask you to imagine the following scenario. Say you live by yourself. There's no other people in the house normally, but you have your bedroom upstairs and there's a living room downstairs, and you wake up in the middle of the night at 3:20 and you hear noises from downstairs. Now, the question is, how much do you need to know to be justified in thinking that there is an intruder downstairs? You know you live alone. You know at 3:20 nobody is supposed to be there. So you definitely don't have, but let's say you hear noises that are so specific that you're sure that there is a human being down there from the kinds of noises that are being made up. So they turned on the TV, they make a lot of noise. And you don't know, you don't have to know the ethnicity, the age, the size, the mass, or the life story of whatever or whoever is causing noise downstairs to be justified in thinking that there is a dangerous intruder downstairs. Of course, you might also be justified in thinking that the source of the noise is your wayward sister who spontaneously came back to town and decided to crash at your place, and she knows where your spare key is. You might be justified in thinking both these things. And in the end, what you will do is to have to judge what is the best explanation for the noises you hear from downstairs, at least while you're still in your bed. That's the best thing you can do. And I think my point is that given certain background knowledge, for example, how far away your sister lives and how seldom she comes back to town, you really don't have to know very much about the person downstairs to be justified in judging that it is a dangerous intruder. And I'm going to compare this to the evidence that we have of the existence of black holes and dark matter and ask whether that is similarly enough to be justified in thinking that they exist. So first, to black holes. Eric Curie.
Dennis,
Yeah.
what if it is a cat?
Well, that's why I added this extra sentence. We're saying, well, and imagine that the noises that you hear are specific enough to be relatively sure that it is a human being. For example, the TV was turned on, like, you know, in Get Shorty, TV is turned on and the mafioso who is there to kill him sits down and waits for him to come downstairs. That kind of scenario. Yeah. But I saw that coming the moment I said it. It could be a cat. Yeah. But not with certain noises. Thanks. Yeah. So now to black holes, right? So you might think that a paper that Eric Curiel wrote 5 years ago, or published 5 years ago, brings up a similar problem, namely the question of whether the concept of black holes that we have is thick enough to refer with regard to black holes. So he points out that different subcommunities in physics work with very different concepts or definitions of black hole, and he believes that there is no common core. He says, I believe that there's a widespread hope across the many fields in physics in which black holes are studied, that though the conceptions, pictures, and definitions used differ in manifestly deep and broad ways, nonetheless they are all at bottom trying to get at the same thing. It is difficult otherwise to see how work in one area is to make fruitful contact with work in all the other areas. It is, however, at this point, only a hope. And I think this seems akin to Niels' starting point, right? Because coming from here, you can ask, do we know enough about what is or should be meant by black hole for it to be a reasonable conviction that they exist, for it to be reasonable to be a realist about black holes? And Eric at least argues that he thinks there is no common core. He says one may conclude after many pages that there is simply no common conceptual core to the pre-theoretical idea of a black hole, that the hopeful conjecture that physicists in different fields all refer to the same entity with their different definitions has been thrown down on the floor and danced upon. I would rather say that there is a rough, nebulous concept of a black hole shared across physics, that one can explicate that idea by articulating a more or less precise definition that captures in a clear way, many important features of the nebulous idea, and that this can be done in many different ways, each appropriate for different theoretical observation and foundational contexts. And Eric ends up arguing that there is some strength in this because it makes the concept of a black hole more flexible, but it raises the same question as Niels raised in the context of dark matter, namely whether in the absence of a strong enough common core, is the term able to refer. And so here are, just very quickly, there's a table from Eric's paper on the many different definitions or core concepts or core properties maybe of what the term black hole refers to in different subcommunities in physics. And so you see here, he distinguishes between astrophysics, classical GR, mathematical GR, semi-classical gravity, quantum gravity, and analog gravity. And so looking at this, I thought, well, I think everything that he says is correct here, but this leaves open the possibility that maybe, at least as far as the empirical domain is concerned, right, not mathematical GR, which is a discipline of math in a way, semi-classical gravity, which is speculative, quantum gravity, even more speculative, analog gravity too, but whether there is a common core concept that is in touch directly with the empirical evidence that we thus far have. And the first shot at this would be the following. So the observationally relevant common core concept of the term black hole could be something like this. It's a compact object with mass and angular momentum whose exterior gravitational field can be faithfully represented, or at least approximated, by the Kerr metric. And thus, it has an event horizon that causally isolates the interior of the black hole from the rest of the universe, so that classically, right, staying in the classical domain, it only interacts gravitationally with other bodies. And of course, this property 4 also makes black holes one candidate of one concrete form of dark matter.
Why does it not interact electromagnetically in this definition?
In this definition, because of this is the term classically, right? Because so if I disregard the possibility of Hawking radiation and I only look at the outside of the black hole, right?
If you have Kerr-Newman,
Pardon?
if you have Kerr-Newman, for instance.
If you have Kerr-Newman, yes, that's true. I could, it's true that I could add that to allow for the possibility that at some point a black hole that has charge, that has electric charge could be found. Yeah, that would be fair to make it slightly more general to allow for that possibility rather than saying that so far we haven't found any. You're right. Would be more cautious. Right. Okay, so in practice, I think when it comes to black holes, specifically that result from stellar collapse, from the collapse of stars, we know that really fascinating and complicated physics is taking place within the collapsing matter inside the event horizon, right? We know there is all kinds of things that might be going on there while the star is further collapsing within the event horizon. And yet we don't have any access to that region, and likely will never have any access to that region. And if we did have access, then only by falling into the black hole ourselves and not being able to tell anybody what we found on the outside. And more, we don't even know how to model the interior, right? There is no interior non-vacuum metric that can be matched to the outer Kerr metric. Very different situation compared to the Schwarzschild metric, which is of course a special case of the Kerr metric. And thus, there are all kinds of things that we don't know about black holes. We don't know what's going on within the event horizon. And this becomes particularly clear when we think about the fact that they are the most massive objects in the universe, and yet we describe them by vacuum solutions to the Einstein equations. That in itself already shows how strong the idealization is that we use. And of course, that idealization only works because of the interior being causally isolated from the exterior, right? So it doesn't do any harm that we don't know anything about the inside because it doesn't have any effect on anything on the outside. So it's cool, but there is all kinds of things about black holes that we don't know, both physically and mathematically.
I sort of want to also a little bit disagree. I'm sorry. I mean, maybe observationally, it's difficult to access if you don't fall in, but mathematically, you can access, of course, the interior by assuming the Einstein equations, which I think is reasonable. And then you study all the problems, what's happened inside the black hole, right? So I think it's
but I mean, I agree, but it would still be the interior of a vacuum metric, right? It would still be the interior of the Kerr metric, i.e., without a momentum source.
Solutions. No. I mean, the power of mathematics is exactly that you don't have to study explicit solutions, but you can study generic solutions. I mean, this is sort of what in the last 20 years sort of mathematicians have done.
I agree. But you do agree that there is no exact solution that describes a non-vacuum interior that matches the exterior Kerr metric, right?
You can construct such solutions. I disagree with those.
But not exact solutions.
I mean, by exact solution, you mean solving the Einstein equation, or do you mean that you can write it down explicitly?
Write it down explicitly. Not numerical. I mean analytic exact solutions, not numerical.
Exactly, the power of mathematics is that you can go beyond what I call explicit solutions. That you can go for generic solutions, and I think it's sort of important. It's exactly the power of mathematics in the last 20 years and mathematical analysis and partial differential equations to study solutions which are more than just something you can write down by hand. And I think it's an important point. So I sort of want to disagree with you, but
yeah, that is fine. And I could be convinced of your position, and it is something. I mean, especially the work of the last 20 years, when it comes to numerical relativity in particular, that's something that I would like to study much more. That's true. Yeah, thank you.
So Dennis, I also have a question on this.
Sure.
So as you said, in the Schwarzschild case, you can find an interior solution.
Mhm.
Some equation of state, you can make a spherical object which matches to Schwarzschild in the exterior. And typical examples have a radius that's somewhat larger than the
Mhm.
horizon, right?
Mhm. Mhm.
But these guys are perfectly fine. They are Schwarzschild in the exterior, and for an observer, there would be no difference unless the observer came very close to the surface.
Yeah.
So in that same vein, if I found a rotating matter object whose exterior is the Kerr metric and it's compact, but not as compact as the horizon, does it fit in your whole story or not?
I think it does fit, because all I want to say is that there's all kinds of things that we don't know about the interior of black holes. We can try to model them, not analytically, but numerically, yes. We can try to model them, but we don't know about all kinds of things that are going on. We can explore what could be in there, but we don't know. That's really all that matters to my argument.
But maybe I want to start again. The bullet point 3 is incorrect. I can prove theorem which states that there do exist such solutions. I mean, there's a mathematical theorem which I
Yeah, I should have said analytic, exact, non-numerical.
This is not numerically. This is this is rigorous mathematical theorem which proves that you can have such solutions. Okay, I mean it's important to understand the difference.
I understand the difference. I have just not come across this result, so I'll have to look it up.
That's okay. That's okay. But it is not numerical
Solutions.
Sorry.
Yeah.
Prashant here has solutions. He's going to probably write a paper on this.
Okay,
We should cite this other paper that you
Wow,
mentioned. Yeah, no, it's
this is
possible
also
to
not
write down.
surprising. It is not surprising.
No, not
This
at
is-
all, yeah.
I think that one confusion is that you can prove something exists without being able to write down an explicit instance of it. I mean, this has been a debate since, for 100
Right.
years in mathematics. And if people wanted to argue in the 1920s that you shouldn't be able to do that, you should be able to write it down explicitly, but they lost that debate.
Yeah.
Right?
Right.
So I think what you're saying is you can prove that such a thing exists, and then maybe perhaps Prashant is going to is going to show that there is an explicit solution, but that's the relationship between those two things. They're not the same statement, but they're closely related.
Okay, so would you say that? So the problem is with there is no interior, read as there is no existence proof, and that you say is false. But the stronger statement, no explicit metric that can be matched to the outer Kerr metric, that you would say is true?
But it's a strange notion in my opinion, because a lot of
It's good enough for you.
mathematics is sort of, I mean, an explicit solution is something which I guess would be particularly that it's real analytic.
Yeah.
Right? And
Yeah.
this is studying real analytic solutions is okay. It's a strange notion, especially if you believe in sort of something like causality, for instance.
Mhm.
If you believe in the causality, then this is in contradiction with sort of a priori assumptions about real analyticity, because real analyticity means that if you change your initial matter distribution at one point, then it will instantaneously change everywhere in the whole universe. And this violates the causality. That is why sort of imposing real analyticity is a strange assumption. And in general, for modeling all kinds of phenomena using partial differential equations, fluids, you don't assume it. So this is my point.
But is that more weird than the notion of the event horizon, where in order to define the event horizon, you need to know an awful lot about what's going on in space-time globally?
I mean, these are two different aspects. Yes, I agree that the event horizon is defined teleologically, as you said. That's how you define it in mathematics. And that's sort of the best definition, and it is what it is. You may don't like this notion, but it is what it is.
Yeah, well, I was just asking whether you would consider that equally weird as, but that's fine. Yeah. Yeah. Okay, thank you. That was very helpful to me. Okay. Okay, so I would say there is yet a lot that we don't know about the black holes. And yet, just as in the case of the intruder downstairs, who has all kinds of properties that we don't know of when we listen to the noise coming from downstairs, we may know enough about them, about the intruder downstairs and about black holes to know that they are there, right? You don't need to know all the properties of something to know that it's there. And in particular, I think, so if we look at the following classical lines of evidence for the existence of black holes, on the one, so three of them, Genzel's and Gates's results about how Sagittarius A star influences nearby stars, LIGO's results on the gravitational waves emitted by the merger of very massive binary objects that don't shine, and the EHT's pictures or images of the gravitational lensing caused by and accretion disks of the super heavy objects at the center of the Milky Way and galaxy M87. I think it can fairly be argued that the best explanation for all these observations is provided by interpreting them as due to the presence of black holes. And also that what I call the observationally relevant common core concept of a black hole is enough to identify them as black holes in all these three cases, right? And so that is then the argument that that definition for black hole is thick enough to say that it's been empirically confirmed by these results. Now, how does that look in comparison to dark matter? So looking again at what I call the observationally relevant common core concept of dark matter, which you've seen before here. Yep.
Quick clarification. So going back to the black hole case, so is this multiple, is the fact there are multiple empirical measurements that have, you're talking about the EHT, in the case of the black hole, does the multiplicity matter? You know, these classical lines, the fact that there are LIGO, is that relevant? I just want to know, because I know where you're going to jump next, but multiple lines of evidence, independent evidence, that's relevant, right?
That is very relevant. So in fact, I think, so this sentence here, best explanation of all these observations, I think that could be spelled out in two very different ways. And one of them is more convincing than the other. I think one could each by itself argue that the best explanation for this separately is that there's a black hole at the center of the Milky Way, that this separately, that it's minor black holes that collide, and this separately, that it's right. So one could do that, but I think the more convincing inference to the best explanation is found by showing, well, it's the same in all cases. In fact, here 1 and 3, it's even the same system, right? So there in particular, the inference to the best explanation is significantly strengthened through the multiple lines of evidence.
Yeah, so you're saying basically that it's the combination of each one of those empirical data being convincing in itself, and then the combination in addition, right? So you need both of these facts. Okay.
Yes, correct.
I'll just add a small comment here. So you could have horizonless compact objects that could also satisfy all these three criteria if they have photon shells. But you would then argue, I think, you would then place theoretical priors saying that these guys are more contrite, or these
naturalness.
Naturalness. Right.
No,
and then you could say
can
that.
you explain the fact of the inferred density in the center, the Genzel gas?
Yes, I think, one of these like Grava stars or something like that, or even other kinds of objects, you could construct them so that they have the same, so that they're vacuum in the exterior. So for the stars, it will not matter at all. For the EHT images as well, you could, I mean, the mass function for some of these guys just drops off so rapidly that you don't really see them even at the ISCO or even at the photon shell. So as soon as you have a photon shell, you could explain at least 1 and 3. In the second case, also, I think it's possible to do. But then I think you would have to invoke naturalness to say that black holes are the best candidates as well. So yeah, there's also that as well.
Thanks, Dennis.
Okay, thanks. Okay, now how does it look with dark matter compared to the lines of evidence of black holes? So there, three major lines of evidence are the first, galaxy rotation curves, right? They are different from than they should be if most of the mass is concentrated in the stars, simulations of large scale structure, formation of the universe, and gravitational lensing, like in the case of the bullet cluster. And here it is more controversial, I think, that the best explanation for all those observations is provided by interpreting them as due to the presence of dark matter. That's just a sociological claim, right? I've seen more people be skeptical of this than about the, yeah.
This list is incomplete because the bullet cluster is not the only case. The
Oh, yeah.
observed gravitational lensing in all clusters and galaxies. So the bullet cluster is really only about the non-baryonic nature of dark matter. So this is
I agree.
a misunderstanding that the bullet cluster people have put out as propaganda. It's not evidence for dark matter. It's for non-baryonic dark matter.
Right. I agree. I did not.
Yeah.
Sorry.
I think you want to expand that to gravitational lensing that's observed in galaxies on all scales, clusters, galaxies, groups, etc.
Yeah, I agree. And I did not mean the list to be exhausted, and hence very consciously chose, like in the case of the bullet cluster, but this is not supposed to say this is the only case.
Right.
But yeah. Okay. But I mean, coming back to what you said before, so one thing that stands out here is that at least relatively speaking, compared to the black hole case, we don't have the same type of convergence as in the case of black hole, where the first and the third were about the same system and providing different lines of evidence for the same system.
That's why I want you to add gravitational lensing by individual galaxies.
Yes.
Okay, so I think I don't buy your thing because you have to clarify third. You cannot choose one that's not going to fit with, because there exist individual galaxies that would have the rotation curves that are actually giving you gravitational lensing. So we've measured rotation curves for the same galaxies that are giving you lensed arcs. We have that data now.
That's a good point. So that means that the similarity between those three is stronger.
To the black hole case.
Yeah. So amended like this, that would be well, at least almost equally strong relationship between A and C as I had before between 1 and 3. Right, that's your point. Yeah.
Yes,
okay.
That's
Thank you.
point.
Thank
Except there is a fly in the ointment, which I trust you are coming to next.
you. Okay.
The fly in the ointment is that there is another explanation for the galaxy rotation curves. However, right, there is MOND and whatever those other theoretical explanations, right?
Yes. Yes, indeed. So that's what I was about to say here. More controversial because at least A has been interpreted with an alternative non-matter model, right? And hence
then the same A, if you go with that explanation for A, it cannot simultaneously and self-consistently explain A and C as I modified it with the lensing by the galaxies that
I agree. And arguably that's the reason why, even though it's more controversial, it's still the majority opinion that dark matter is at play in all three cases, right?
Right, and that the alternate theories are unable to actually account for gravitational lensing on any scale. They cannot explain that phenomenon without adding extra mass.
Yeah.
In some other form, like neutrinos or some other unseen mass, which then destroys their explanation of getting rid of unseen matter to start with, right? Yeah.
Yeah. Yeah. Thank you. Okay. So I think with the amended list, but even with this original list, I think it is fair to say that, as in the case of black holes, the observationally relevant common core concept of dark matter is enough to identify dark matter as it appears in this list of lines of evidence. as such in all three cases, right? That it is, in fact, and even more, that these three cases identify the dark matter that plays these explanatory roles as the dark matter that occurs in lambda CDM. So, oops.
I concur with your conclusion.
Right.
Yeah.
Good. Okay, so now, how do those two lines of evidence compare with regard to the existence of black holes and dark matter? I'm very curious to see what you say about this. So if we come back to the case of waking up at 3:20 and wondering whether there's an intruder downstairs, as I argued, it's surely reasonable, even while you're still in your bed, to think that the noises coming from downstairs are due to an intruder. But how much do you have to know to be sure, right? And so far, we've established that given the evidence and explanatory successes delivered by assuming that they exist, it is reasonable to be convinced of the existence of black holes and dark matter, respectively. But the question is the evidence strong enough for it to be also unreasonable not to be convinced that they exist? Right? In the intruder case, I think the point where it would become unreasonable to think, well, maybe it's my wayward sister who's trying to crash in my place, the point where that becomes unreasonable is the moment when you have direct evidence that there is an intruder downstairs. For example, by actually going downstairs and seeing a strange man with a smoking gun in his hand. And the question is now whether the evidence just presented for black holes on the one hand and for dark matter on the other hand is direct enough for it to be of smoking gun caliber. And here I'm turning to a recent paper by Jamie Elder, who tried to make a definite distinction between direct versus indirect measurements. And she starts by discussing earlier work by Alan Franklin, who she diagnoses operates with 4 different ways of spelling out the distinction between direct and indirect measurements, observations, evidence, which she then calls the no interference view of directness. So measurement is direct if there was no interference, roughly speaking. The degree of directness view, which argues that there is different degrees of being direct or indirect, rather than it just being a binary distinction between direct and indirect measurement, observation, or evidence. The dispensability of statistics view, which I won't get into, and the intuitive view of directness. And her own view, as applied to the LIGO results in particular, is a refined version of this intuitive view, which itself states that a measurement is direct when the phenomenon or the signal measured interacts directly with the measuring apparatus. And spelling that out further than I have here, Elder concludes that LIGO directly detected gravitational waves, but indirectly detected black holes. And so I'd like to get a bit more into this and ask, so how indirectly? How indirect is the evidence for black holes provided by the LIGO results and by the other lines of evidence? And in the following, I'll assume that even though a quantitative degree of directedness account might not work, because Jamie gives very convincing arguments against this option 2, a comparative account where we say, well, we might not be able to say quantitatively whether something is more or less direct, but we might be able to say that this is more direct evidence than this, and that might be instructive. And so if we have again, so here the 3 types of evidence for black holes on the one hand, for dark matter on the other hand, and then here and here, I'm really trying this out, and I'm curious to see whether you agree or disagree. I would argue that 1, Genset's and Gates's results is more direct evidence than B, large-scale structure formation, involves simulations more strongly, and similarly direct as A, galaxy rotation curves. 2, on the other hand, the LIGO results, only as interpreted as evidence for black holes. LIGO's results is more direct evidence than both A and B. And a single case of 2, right, 1 detected gravitational wave with a gravitational wave signature that corresponds to a gravitational wave template and hence can be associated with 2 particular with two black holes of particular mass is similar direct as C, but I'd say there are many now, right, in the last few years, many more concrete cases of 2 than there are of C. Now I'd be very curious to hear whether you think that's true or whether that has been sort of become not true now because of the gravitational.
I have a comment here.
Okay.
So the left column on the black holes, they are all excellent proof that we have compact massive objects.
Mm-hmm.
The EHT, for instance, constrains the radius of this compact object to be very small inside the photon orbit. So if you're saying that you're asking, do we have evidence of compact gravitating objects? Absolutely, these are all highly compelling. But that's not a black hole yet, right? Prashant already mentioned, there are these black hole mimickers, which are not black holes, but still very compact, gravitating, etc., which to the exterior universe look like a black hole. So I think it's that last step, going from the evidence for compact massive objects to calling it a black hole, which is where I think you need to come up with some belief system. You have to say what is natural, what is not natural, etc. So I was wondering how you're kind of negotiating that final distinction.
Well, it's exactly because of that type of worry that I only wanted to say that which of those lines of evidence is more or less direct evidence for the existence of black holes compared to these lines of evidence. I'm not saying absolutely conclusive evidence, no other model is possible anymore, right? I'm just saying it makes the case that it is a black hole stronger and stronger, these 3 results, than each of them by themselves. That there are still possibilities that actually it's a compact object that is not a black hole, that I think is not at all excluded by this, which will be part of my conclusion at the end.
Yeah, but isn't it exactly the same on the right? There are these other models which say there is some modified gravity that explains your all the observations. I agree that there is a problem with the gravitational lensing.
And B and C.
Or B as well.
Yeah, they cannot reproduce C and B.
Fine. Okay. So the alternate explanation is more dicey for the dark matter compared to the black hole. And so would we therefore say dark matter is much more likely?
But with the sorry.
Yeah.
Yeah. So I mean, I would say it's the evidence that it might be black holes is more direct than the evidence that it might be dark matter.
John has his hand up, and then I'll speak. Yeah, I've spoken to what.
Hi, thanks for the excellent talk. I just want to make a comment about point C, that not only are there lots of examples of gravitational lensing, there's also many more examples of clusters than the bullet cluster where the X-ray emitting gas and the dark matter, or let me be more precise, the gravitational lensing signal are separated on the sky, which is an evidence for the lack of collisionality of the dark matter. So this is where I would maybe dispute the point where there are many more concrete cases of 2 compared to C, because we have many more examples these days of what we call the dissociated mergers, where the 2 signals are clearly separated on the sky.
Okay.
Yeah.
Okay, that's very interesting. Thank you. And would you say, so that is about the number of cases, right? So
yes.
And which I say, so I have here 2 aspects to this claim. So the first aspect is, are there more cases of gravitational waves emitted by binary black hole mergers versus gravitational lensing cases in galaxy clusters? And the second aspect is, if you compare an individual case, one gravitational wave emitted by binary black hole, would you say that is more direct evidence or equally direct evidence compared to one gravitational lensing case in a galaxy cluster?
I mean, I would want to venture that so the observations in C are, I want to speak carefully, easier. In and that their order of magnitude, the number of observations in 2 or C are probably very similar, but there might be more in C. But this is just a guess because I'm not an expert on LIGO, of course. And the other, it's probably fair to say that C is less direct, but then, you know, it's a direct measurement of gravitational lensing, that's for certain. So this is where you get into parsing words a lot.
Yeah, no, it's clearly direct evidence of gravitational lensing, but less direct evidence that the lensing is being done by dark matter of lambda CDM.
I think there's just a couple more slides of conclusion, then we can maybe come back to this. Would that be okay?
Yeah.
Okay, but I think it's important.
Yeah.
I wouldn't be speaking if it wasn't
No.
important. Thank you. So I think 2 and B are equally compelling because you're using templates, and large scale structure is also using a model to a convolving model to give you the CMB and isotropy map. So I would say they are equally direct because there you're using templates anyway in 2. And similarly, if you modify and expand C the way I thought it should be, include gravitational lensing by individual galaxies, etc., not fixate on the bullet cluster or many instantiations of mini bullets, as John pointed out. We see many, many cases of crashing clusters. But if you expand the category, I think C, C is much more direct than 3, because the EHT can be seen as like, one particular instantiation, right? So here, there are many, many different kinds of objects that are simultaneously giving you no other way to produce the arcs other than dark matter. So.
Right. Great. Agree. Very important. Thank you very much. Okay. Yeah. And, but you were right. There was only 2 more slides. So here, I mean, I really put this here to get your feedback on this, because it is a very difficult comparison, right, of, comparative analysis of directness. And I'm aware that this needs to be spelled out much more and argued for with more time and caution. If we come to the conclusion that together this is more direct evidence for the existence of black holes, then this is evidence for the existence of dark matter, then it would follow that even though it is reasonable to believe both in the existence of black holes and dark matter, it is less reasonable to disbelieve the existence of black holes than it is to disbelieve the existence of dark matter. Now, how much less reasonable depends entirely on how close the directness is here. Okay, that brings me to the conclusion. We know enough about the concepts black hole and dark matter to know that it is reasonable to be convinced of the existence of both of them, and we even know to judge that their existence is the currently best explanation for a series of observations, and that these observations confirm the core concepts of black holes and dark matter. We also know that the dark matter concept inherent in lambda CDM is at least as thick as the matter. This is something I haven't mentioned yet, but at least as thick as the matter concepts with which Einstein and Friedman started relativistic cosmology, where they assumed the matter in the universe to have the properties of a dust fluid or perfect fluid, respectively, the former being collisionist fluid for which no particle constituents are assumed, and it not interacting electromagnetically. Of course, that was only supposed to be a stepping stone, right? Einstein in particular was convinced of the incompleteness of the concept of matter as it appears in GR, and he always assumed that we would eventually learn more about the nature of matter than GR by itself as a theory of gravity would ever be able to tell us. So indeed, similarly today, we surely know far from everything about black holes and dark matter, but just as we don't need to know much about the person causing the noise downstairs to be reasonable in thinking that they are an intruder, we don't need to know even nearly everything about black holes and dark matter to be convinced that they are there, and thus to be realists about both black holes and dark matter. Still, arguably, and to be spelled out, the evidence for black holes is more direct than the evidence for dark matter, and thus it is less reasonable to be convinced that black holes don't exist compared to being convinced that dark matter does not exist. Though I would be very excited if this could be evened out. Okay, that's it. Thank you.
So maybe let's have Niels's question first. Yes.
Okay. Hi. Yeah, so I have two related questions, which kind of stem from the paper by Weinberg, which I also found very interesting. So the first thing I found interesting about the paper is that they bring in the term unique natural kind. And the second thing is surprising, was that helped me clarify my thoughts, even though I guess that term is in itself also a bit more vague than most philosophers who use it think it is. But it also, the second thing that surprised me is that I then thought, okay, that's great. This is good nomenclature to explain that I think the current common core concept is not a unique natural kind, and Weinberg thinks, no, it is even though it's agnostic as to whether it's a particle or not, that's a unique natural count. So I guess the first question is, do you think both of these cases, the black hole case and dark matter case, are unique natural kinds? Because with the black hole case, I feel like if you put a gun to my head, I'd probably say yes, although I share Ramesh's black hole mimic worries. And also, if we detect a photon ring, we would really know much more about black holes, are they GR black holes, and we don't yet know it, so it feels like something is missing. But the dark matter case, I want to say, no, that's not a unique natural kind at all. It's at best a disjunction of many, like primordial black holes, fuzzy dark matter, etc. So to me, it seems like it's not a unique natural kind, and that's to me that's grist to my mill. And then secondly, if you agree with that, then isn't it inappropriate to say that these are the best explanations? Because to me, it seems like more it's a disjunction of many potential explanations. To even call it best explanation as if it is one explanation seems to be not appropriate to me. It's just a disjunction of this.
Yeah, it's a good question. I mean, I'm afraid I don't believe in the existence of natural kinds, full stop. I just don't believe in them. And so hence, in a sense, the question doesn't ask itself to me. But if I put myself sort of in the shoes of somebody who believes in natural kinds, then I would also say, at least intuitively, but given that my intuition will be weak, given that I'm not convinced of it, that the term or the black holes have a better shot at being a natural kind than dark matter. But how I exactly would justify this, I'm not quite sure. Yeah.
Fair enough.
Yeah. Thank you.
Question, but there are others ahead of me. Okay. On a philosophical level, I think it's quite important. I mean, I think there's an important point that you're making, Dennis, which goes back to issues a long time ago with Thomas Kuhn in the 1970s. At one point, Kuhn, sort of retreating from or modifying his scientific revolution idea, said maybe we need to have micro revolutions. And the idea was that you had some entity which you think you've seen, and you discover some new property of it, like you discovered that the electron has spin. And so you say, well, that's actually not the same thing as the electron that doesn't have spin. So really, we're in a different world of the ontological, the nomological, and the epistemological, the three sort of criteria that he had for identifying a paradigmatic instance of science. And you really should talk about each change in the ontological status of the object, that is to say, each list of properties that have been established or are supposed to be established. And the problem is that this leads to a kind of deterioration of, or an extension to be every little thing you discover about a particle, an animal, whatever it is that you're looking at, is a new revolution. And then the idea of a revolution sort of loses its bite. It no longer is interesting philosophically, So I think the broad goal that you have of saying there ought to be some characteristics of an entity that we can be realists about, even if we don't know all of its properties, seems like it must be right, or we'll never be able to say anything, because properties will constantly be added to those things that we know. Certainly that's true of things as complicated as, black holes, if you include the interior characterization of them and so on. So, and then I guess the discussion here has revolved around the status of, where to put that marker. Where do you put, what is enough thickness or fullness of description to be able to make a realist claim?
Yeah.
So certainly we spent a lot of my life worrying about mimicking events, whether it's in my history and philosophy of science or in the physics of the black hole with EHT. I mean, we worry about these things. Also, anybody involved in the empirical side of science worries about mimicking effects. That's ultimately what an experiment that is making an existence claim has to be concerned with. But how far one goes and whether one says sub specie eternitatis or where one says that is the crucial matter. Thank you.
Yeah. I agree with everything you said, and I think, yeah, it's difficult to say where exactly you draw the line to say now I know enough to know that it exists. My feeling, even though I didn't focus on this, is that it is that line is first of all it might shift, right? If you have completely new lines of evidence, where you draw the line might shift. But in general, I think it will be related to multiple lines of independent evidence, as we have in both cases here, right? And yeah, thank you. I agree.
Okay, so there's 2 more hands on Zoom, so if we can keep them short, but let's do Gally first.
Hi.
Hello.
I'll try to be short. Ian Hacking suggested a wholesale skepticism about black holes because they do not fit his entity realism embodied in his slogan, if you can spray them, then they are real. Now, in his he contended in 1989 that gravitational lenses were dark matter. He called black holes, which do not exist. What do you think about Hacking's philosophical stance?
I think it's too restrictive. I think to say that you have to be able to not just manipulate them, but manipulate with them. I think that's too restrictive for knowing that something exists. I think, especially when we have different lines of evidence about something that all fit together, even if we can't manipulate it or manipulate with it, we can have enough evidence to believe in its existence. So that is in direct contradiction to Hacking. Yeah.
Okay, and Tyler.
Sorry. Can you hear me?
Yeah.
Hi. So I have 2 short questions. So you relied a lot on 2 concepts. One is IBE and the other is directness. So at some point you said that in the case of black holes, those lines of evidence, each of them can be seen as a kind of a case of IBE. And then you said in general, the collection of them can be also explained as a kind of a case of IBE. So the question now is that you didn't say anything about the of IBE itself, which there is a lot of literature about it. If the skeptic doesn't buy your argument at the first place, then the second order of IBE would be not acceptable at all for a skeptic who doesn't believe the reliability of IEB. That was the first. And the second is that the concept of directness. So I think that when, like, I'm having a paper about this direct indirect distinction. So I think one should be careful about making a distinction based on the methodology that something is direct or not and the epistemic significance of it. I don't think that's always the case. That I don't think that there is an epistemic concept of epistemic directness access to something. It's all based on the method that you are using. So not always the methodological distinction kind of has the same epistemic significance. Sometimes maybe the indirect observation is epistemically more significant. So that was just, yeah. What do you think about that?
Okay. Let me answer that part first. The second question about directness. My expectation is actually that, and remember, right? I didn't give any absolute distinction between direct versus indirect, but only a comparative notion that some bit of evidence might be more or less direct than another bit, right? And my expectation would be that more direct is in general better, right? More direct is in general better evidence for the existence of something, at least for existence claims, than less direct evidence. So I would throw that back to you and say, well, give me an example where indirect evidence ended up being a better bit of evidence than direct evidence. I would love to see it, but I can't come
There
up
are
with
plenty of examples, actually. My exact problem is with this general distinction. Like, generally, I don't think that directness is epistemically superior to indirectness. So even in the case of perception, sometimes indirect, like when you're looking at the moon right now, like the telescope is much better than naked eye. Although like the telescope might be conceived as indirect, right?
Yeah, but I mean, it's only better because we have lots and lots of reasons to trust it, right? If you, when the telescope first came around, that was in a way the big discussion between Galileo and the Jesuits. What is the telescope trustworthy in giving us a picture of the heavens? And it was not unreasonable, at least for the first, one can debate for how long, but not to trust it immediately, right? So it depends how much, if you have a lot of direct evidence that the telescope is trustworthy, not just on Earth, but in giving us a picture of the heavens, then that, I would say, carries over to it being reliable and maybe even more reliable than your naked eye. Yeah. But so that is not, I would say, a case where by itself the indirect evidence is better than direct evidence. It's conditional on all these other reasons to trust the picture of the telescope more than what you see with your naked eye. Yeah.
Yep.
Yeah. And the first question about IBE, yeah, I agree. And it's for lack of time that I didn't get into it, and also because I thought, I'm opening a hornet's nest because it's a big and beautiful discussion about how IBE actually works, what kinds of IBE there might be, especially how to spell out best, right? And also how to restrict the candidate pool from which you choose the best explanation. And there's all kinds of things that can go wrong with it. And I agree, that's a fair point. And it's only that, yeah, sometimes it's the best method we have in a particular domain, right? And so I think it's still worthwhile to check which role it plays, in fact, and I think it plays a huge role in scientific practice. And that's I only see my role as trying to understand the role it plays, rather than arguing that is absolutely trustworthy or not trustworthy. Yeah.
Great, thanks.
Welcome.
Join me, everyone, in thanking Dennis again.
Thank you very much. That was very, very helpful for me.